So let's start today's discussion. So in the previous lecture, we have actually obtained the mode expansion, the normal mode expansion of the electromagnetic free vector potential, and we were trying to uh, do the calculations in the Coulomb gauge. And in that particular gauge, what we found was the following. If you recall, we found that, and we had put the field, electromagnetic field, in a box of volume field, and there we found that the mode expansion can be written as written in the following form: is C4 pi volume G, the structure, and then we have this and 1 by 2 k square root. And then we have epsilon vector equal of I x minus omega k plus, you can keep epsilon vector outside. Then we had epsilon vector complex conjugate because of this form. So we wrote something like this, and we also discussed the possibilities of this plane electromagnetic wave to have polarizations, linear polarizations, in which the epsilon vector becomes the unit vectors 1, 0, 0 or 0, 1, 1. So this is linearly polarized plane electromagnetic wave, and the other case where epsilon vector can be, where the polarization can be circular polarization, and there the epsilon vector is something like this, where lambda is plus or minus, and epsilon vector plus was, if we normalize these polarization vectors, then this you can write it down in this way: 1I0, and epsilon vector minus, you can write it 1 by root 2, 1 minus I. So these are the two independent states of polarization, and this is the polarization picture is in the case of the classical electromagnetic wave, whereas if you go to the, if you interpret light as something quantum, then you have to interpret these as photons. So we have not yet gone to the photon picture of electromagnetic wave, but here what will happen is the following: that these two independent states of polarization will actually correspond to the angular momentum projections of the mean angular momentum of the photon along its linear momentum. And he also noted the following things: that epsilon vector dot epsilon, this is lambda, epsilon star lambda, that is equal to delta lambda lambda prime. What we do is we now move on to the quantum case. Let us move on to the quantum case and write down the mode expansion, normal mode expansion, or the Fourier mode expansion of the radiation field operator. So let us now, right? So in the case where this field is a quantum field, then this particular thing will become an operator, will be elevated to the status of an operator. So I just put a hat on top, but you can also get rid of that. So you just remember that this thing now in the quantum case is an operator, and therefore the mode expansion, or the normal mode expansion in this case, will be of the following form. See, these were the actually the solutions of the wave equations of the wave equation satisfied by the vector field by the vector potential. So we wrote this the general solution in terms of the in terms of a particular mode in terms of the solution which corresponds to a particular mode K. And now in the quantum case, again we shall expand these in terms of these normal modes. So that is why this is called a normal mode expansion. So these are the normal modes. And in the quantum case, we shall expand this field operator in terms of the normal modes. And the expansion will be something like this. You have the standard factor that you had earlier in the case of real scalar field. Then we shall have this operator, it's A, K, lambda. So lambda takes care of these two states, independent states of polarization. So you have now actually they correspond to the two angular momentum projections of the spin angular momentum of the photon. So this is A hat K vector lambda, and then we have epsilon vector lambda. So this already you have, so this will also be there here, and now you have this thing minus I omega K T minus K vector dot X vector. So this is an electromagnetic wave which is propagating around the direction A and n cap. You can take that direction to be the z direction, and then you will have a complex conjugate of this term. So it will be A hat dagger A vector lambda epsilon vector lambda once again. Then you have a star, take the complex conjugate, and then you have I omega Kt minus A. This is the complete mode expansion of the field operator. So this is what it is. So this is the quantum case. You are correct. There will be a sum over lambda which I missed because there are two independent states of polarization. There is a summation over lambda. So the summation over lambda takes into care the two independent. You have to sum it over the two possibilities that you can have for the electromagnetic field. And what you can do is you can now postulate that A K lambda and A dagger A prime lambda prime is equal to delta A prime delta lambda prime. And all other A dagger is 0. So this is our postulate. And what you can do is you can check what is the canonically conjugate momenta to this field A. You can actually calculate it, and then you can calculate the commutation relation between this and the canonically conjugate momenta using this commutation relation and see what happens. You will get a Dirac delta function there, and that will be the only non-trivial commutation relation between this field in the configuration space and its canonically conjugate momentum. So they will not commute. Those will be the equal time commutation relations. What we shall do today is the following. From this mode expansion, we shall actually compute the Hamiltonian operator. We need to get the Hamiltonian operator, and we shall do the computation of the Hamiltonian operator. So let us do that. This is actually, the philosophy is the same. The calculation is very similar to that which we have already done in the case of real scalar field, but I want to do it in this case because this is a little bit non-trivial, because this is a vector field and you have this polarization vector, the sum over this polarization, the two possibilities of polarization and all these things. So it is better to do this calculation and see what happens. So if you remember, the Hamiltonian, classical case, it is given by 1 by 8 pi. This is in the unrationalized units. dq takes, it is E vector square plus B vector square. So let me just write it down. E square plus B square. And that you can actually write it down as 1 by 8 pi integral q takes. E square is nothing but 1 by c square a vector dot square, and this is nothing but curl of a whole square. So what we need to compute is the following. We need to first calculate what a dot is, and that is a simple thing to do. The mode expansion has been already given here. So a dot will be c into 4 pi and then we will have summation over k 1 by 2 omega k thing. Then we have k hat k lambda differentiate with respect to time, so I will have a minus I omega k epsilon. I am always missing the summation over lambda, so there is a sum over lambda epsilon lambda e to the power of minus I. Let me write this down as I k dot x, where it means that the k0 component is omega k, which is related to k vector. Let me am writing it down in this way, and then we will have from the other term, on this term, what we shall have is the following: plus k hat dagger k comma lambda I omega k epsilon lambda e to the power of this star e to the power of I k dot x. So this is the mode expansion for a dot. You can see the full board now. Just have a look at the full board. So this is the mode expansion for A, and this is the mode expansion for A dot. Okay, and therefore, now we need to calculate what A dot square is with a factor of 1 by c square in front. So 1 by c square A dot square x comma p will be, we have the mode expansion for that thing. So c square will get cancelled. We will have a factor of 4 pi in front, and then we shall have summation k vector comma k prime summation lambda comma lambda prime. Then we shall have this divided by 2b 1 omega k prime square root comma lambda. So this we can actually take it out. This will become write this as minus I omega k, take that common, then epsilon vector lambda e to the power of minus I k dot x minus A hat dagger K comma lambda epsilon star lambda into the power of I of x. So this is the first term, and then this will be dotted with, you have a dot product, and then you have to write on the same thing, but with k and lambda replaced by k prime and lambda prime. So this will be k prime. So from there, what we shall have is this minus will remain. You can put this minus outside, and there will be a omega k prime, and therefore there is a square root. So ultimately, what will happen is the following: we will have omega k. So this will become omega k prime root. Okay, and then we will have k prime comma lambda prime epsilon lambda prime e to the power of minus I k prime dot x minus a. I'm writing the hats in some places, so let me remove the hats now. So this will become a dagger a prime comma lambda prime epsilon star lambda prime because I. So you have this thing. So this is what 1 by c square a vector dot square is. Is this okay? Is it okay?
Sir, there should be omega k squared actually on the numerator.
Omega
K square.
Omega k, no, it will not be omega k square. Just a minute. I will come back to you. I will come back to you immediately. Only thing is that h bar. If you only thing that I have missed is it is better to keep a h bar factor also over here. Square root of this. Only thing that I have missed. So there is a h bar factor, and correspondingly you just incorporate h bar factor at other places also. So what will happen is this 2 that you have outside, this 2 you can actually put it inside and write this as h bar by 2. No, this will not be omega k square. I will come because what you are doing is.
So not that I am saying on the numerator there will be 2 omega k contribution because of a dot square.
No, that is what I am writing as omega k prime square root.
So that is already there. I am saying when I am doing a dot, there is a minus of I omega k coming before a dot.
Right. That is what I have taken in this way, because before you have a 1 by omega k downstairs.
Yes.
1 by square root omega k downstairs.
Okay, I understood you.
And then 1 by omega k prime, and from there omega k and omega k prime, so that gives you this factor.
Okay.
Okay. Good. So now what we need to do is just multiply these two things. It is a straightforward multiplication. There is nothing much to do here. I will just put in the factor of h bar here. So we need to multiply and see what happens. This is a bit of a tedious calculation, but once and for all we should actually do it, because this is a calculation which involves a vector field, and therefore it is a little bit non-trivial.
Sir,
Yes.
so shouldn't be there in the e to the power I omega k t terms? I mean, why should these terms?
I have written e to the power of I omega k t terms. Here, they are here. These are
Oh, that is not vector. That is,
no, actually,
I mean, that is 4.
that is 4. That is not vector. K dot.
Yeah, okay.
I actually combine
Okay.
power of I omega kt minus k vector dot x as e to the power of I k.
Yes, sir. Okay, I thought it is vector. Okay.
So now this will be what we need to do is just multiply. So if you multiply, this will be minus 4 pi by volume V summation for k prime summation lambda comma lambda prime h bar by 2 omega k prime square root. So these are all about the factors, and then we just need to multiply this thing. So that will be straightforward. It's nothing much. It will be a comma lambda. You just write all the a's together, so that you can keep track of them. So this will be this. The first term will be this. Then it will be epsilon vector lambda dotted with this is a dot product between two vectors now. Epsilon vector lambda prime. Okay. Then we will have e to the power of minus I k plus k prime dot x. So this is this term multiplied by this term. Then we will have minus k dagger k comma lambda k prime lambda prime epsilon vector star lambda dot epsilon vector lambda prime. Then we shall have e to the power I this is the second term. Then this term multiplied by this, that will give us minus a lambda a dagger a prime lambda prime epsilon lambda star lambda prime e to the power of minus I k minus k prime dot x, and then we have the last term, which is this multiplied by this. So the last term will be plus a dagger k lambda a dagger k prime lambda prime in epsilon star lambda dot epsilon star lambda prime. And then e to the power of this into e to the power of I k plus k prime dot x. So that is all that we have. Okay. So let us now so this is the calculation for a dot square, and what we now need to calculate is curl of. So what we now need to calculate is this term is curl of a, and just square it up and then see what happens. So what we can do is we can again remove this side of the board. So let us do the calculation for curl of a whole square on this side of the board. You can actually, you have to remember that now you have to integrate this term over d cubed x and volume V, okay? The special integral will be over a volume V, and that will be so all these terms, this term, this term, this and this x integrals, you will get V delta k prime, and therefore after integration, as usual, what you will have is one summation will go away, this will go away, the k prime will go away, and here for this term you will have e to the power minus I2 minus e to the power minus 2I omega k dot t. Similarly for the last term, and these terms, the omega k will go away. So you remember that you have to do a x integral, it is a volume integral over this expression. Now, curl of A, if you look at the mode expansion, what you will get is a I k vector cross with epsilon. And therefore, if you just square it, which is nothing but b vector square, so that will give us c square 4 pi. So you will have this factor, and then the volume factor will go downstairs. Then we shall have summation k on k prime, summation lambda on lambda prime. Then we shall again have h bar by 2. And here, in this case, we have to be careful because you will obviously have this factor downstairs, omega k prime will be in the denominator now. So this will be here. And then we shall have, if you take the curl, so that will give us the following thing. What we will get is a ik. So you can take a, so you will get an I from here, so that will give us a minus sign in front. When you square it, it will give you a minus sign. So it will give us ik comma lambda k vector cross epsilon lambda. So this is the first term, and then as usual we will have e to the power of minus I k dot x. Then we shall have, from that term we will have a minus term. So we have a minus k dagger k comma lambda. Then we will have k cross epsilon vector star lambda e to the power of. So you can see how complicated this calculation is. This calculation is really a little bit non-trivial. So it is good to go through this calculation. So this is for one of the curl of A, but you have to square it up. So you have a dot product now. So you see that here there is a cross product. Then you have to take a dot product. So this, which is simple to write, not that difficult. It is a prime and a prime, u vector prime cross epsilon vector and the prime e to the power of minus I and x minus k dagger k and lambda prime k prime cross epsilon star lambda prime into e to the power I and x. So this is the full expression. Now what you have to do is multiply these things and you will get 4 terms. Okay? So you will get 4 terms from here. So let us see what can we do with these 4 terms. I will just remove this part of this part and I will do the calculation on top so that you can see the full. So let us look at any one term now. Suppose I multiply, let us take this term, which is this, the multiplication of this term with this term. The first term in here. So this term is basically summation k prime, summation lambda, comma lambda prime, a k lambda, a k prime lambda prime. Then we have e to the power minus I k plus k prime dot x, and we obviously have this factor also. You should always remember that there is a factor of h bar by 2, and here we have a factor of omega k prime square root in the denominator. This factor is always there, this factor. This, and then k cross k vector cross epsilon vector lambda dot product with k prime cross epsilon vector lambda prime. So this is what. And on top of that, you should also remember that there is an integral over volume V dx. So this actually you can do it in a straightforward manner, because all these terms, they do not have any x's. Only term with x is this term, and therefore this integration will actually give us, if you just put the integration inside, so we have an integration. This is nothing but e to the power of minus 2I omega k t volume v delta k comma k prime. So from this integration you can see, now the full integration of the first term has been carried out. You can see that one summation over k prime will go away. The volume factor which is there in the denominator of this term will get cancelled. And this feature will happen in all the terms. The volume factor will get cancelled from all the terms. It will be independent of the volume in which you have put the electromagnetic field. A non-trivial thing, not quite non-trivial, is to calculate this thing. And this, it is straightforward to calculate. This is like A dot B cross C. Therefore, what we can do here is just apply. So you can write this thing as K vector. You can replace this by a dot product and replace this by a cross product. So this will become epsilon lambda cross K prime cross epsilon lambda prime. This is what we shall do. This full thing is this thing, k dot epsilon cross this. Now this is A cross B cross C. So you just apply your high school formula, back minus cap, A cross B cross C. So this will be k prime epsilon dot lambda dot epsilon lambda prime minus cap. So epsilon lambda prime, this dot this. So this is epsilon vector lambda dot k prime. So that completes the calculation. But you know that the polarization vector is perpendicular to the direction of propagation of the electromagnetic field, so that term is 0. And therefore, what we have is k dot k prime epsilon lambda prime from the first term. Okay? And since delta k prime, there is a Kronecker delta, so ultimately what we will have is one of the summations over k prime will go away. This Kronecker delta will go away. This will not be here. this k prime will become mind you, so this will actually give a k vector, not k vector comma k prime, rather k vector is comma minus k prime because of k plus k prime. So you will have a minus sign. We put a minus. You will get a minus because this is k plus k prime. That should be 0. K vector plus k prime vector should be 0. So k vector is minus of k prime vector. So from here you will have k vector replaced by minus k. So this will give you a k square. So you have a k square. This will become minus omega of minus k, but omega of minus k is omega k. Therefore, this full thing will become omega of k. You should remember that there is a factor of 4 pi outside and also a factor of c square outside. But c square into k square, that will be omega k square, and therefore this omega k and omega k square will get cancelled, and therefore you will have the omega k on top. So this is also gone. This term is also gone. And you have a minus sign from there, so you put a minus sign here. But that minus sign and this minus sign will give you a total of plus sign, right? Because there was an overall minus sign, and this minus sign you just get from the multiplication of these two terms without this minus sign. So you have a minus sign coming from there. So minus minus that gives you a plus. So now you just compare that term with the term that you have obtained, the first term of a dot square integrated over here. You compare it with this term, and also a k prime, this will become a minus k. So we'll see from here that this comes with a plus sign, a minus k, and this term will come with a minus sign in front because there is a minus sign here. And therefore, this term that you get from a dot square and the first term that you get from curl of a square actually cancels. So this term will cancel each other. And similarly, you can show that a dagger term from here will also cancel the a dagger term from here. So that a dagger and a these terms are cancelled. That we have shown. Now what we need to show, or we just need to clump in the other terms. The other terms are quite simple. So let me just look at one of the terms because we have a class now. Professor Lahiri will come. So we have to we just have 5 minutes more. So we just take a look at the full board now. This is a dot square term. So here you only have this term and this term to be the surviving terms. So let us look at one of the, or let us write down the full term d cubed x 1 by c square a vector dot square x comma t. Let us write down this term. So this is equal to therefore 4 pi by volume V minus sign. So that minus and these two minus signs will get absorbed. So that will become a plus. So this is summation over k prime, summation over lambda prime. And if you integrate this, what we will get is a Kronecker delta. So we will get a volume V delta k prime. Integrate this over x, you will get this thing. And then we will have a dagger k comma lambda a prime comma lambda prime, and then here the polarization factors. I will zoom the board in a moment. Just wait, you can see, you will be able to see the full board. Epsilon star lambda dot epsilon lambda prime. This is the first term. The second term, okay, let me just, this factor will be common. So we have this. The second term will be a lambda a dagger a prime lambda prime epsilon lambda. Okay, let me now zoom the board. Okay. So when you carry out the integration over x, this will be the thing that you will get. Now you can apply the dot product relation between the polarization vectors. You remember that this is nothing but delta lambda lambda prime, and similarly this is also delta lambda lambda prime. And therefore, what will happen is that if you use that, one of the lambda primes will get cancelled away. And you also have a factor of h bar by 2. I missed it. You have this factor of h bar by 2. Let me keep this factor. So lambda, this will go away. This will become lambda. And this will also become lambda. So this full factor is gone now. We have carried out the summation. And so what remains is the following: omega factor. Huh? Omega factor. Okay, let me just check. Obviously, there will be some factor of, so there will be omega k here. K over here. So ultimately, the final expression is nothing but 4 pi by volume b summation over k vector summation over lambda h bar omega k by 2 volume factor. So volume also gets cancelled. So h bar omega k by 2 k dagger k lambda a k lambda. Polarization summation is gone. That factor is gone. And this similarly you have this factor. In the next class, we shall complete this calculation and go over to another thing. Before discussing the Dirac field, we shall just look at the curl A vector things. We shall write down the other two terms and just add it up. You can actually complete this at home. This is not very difficult, because what you need to do, you just need to calculate this k cross epsilon and dot with k prime dot epsilon lambda prime. So you calculate, as I have showed you, do the calculation, and what it will turn out that everything will add up. These two factors will go away. Those two terms coming from curl of a whole square, and these will add up, and these two factors will get cancelled. And you have to remember that the full Hamiltonian operator is 1 by h pi. So you will get what? H bar omega k, 4 pi by 8 pi will give you a factor of 2 in the denominator. So it will be h bar omega k by 2, a dagger this plus this. That will be the result, and then we will simplify it. Let us complete at this point for today, because now it is Professor Lahiri's class. So if you have any questions, I will address it in the next class. Thank you very much for today.
Thank you, sir.